Hi, good afternoon, everyone. I'm Seema Sundara. I'm work with the MySQL HeatWave team. And I think you might have seen there is a recurring theme in all the talks about autopilot features in MySQL and MySQL HeatWave. So we will delve into those features into a little more detail in this talk. And, sorry. So what we'll go over is we'll give you an overview of the various features available in MySQL Autopilot. Then we'll talk about the autopilot features we have for the OLTP side, that is the MySQL side. Then some of the autopilot features for OLAP or HeatWave. Then we'll talk about some of the autopilot features which are coming up for the Lakehouse feature, and then wrap up with the summary. So this is a general slide we have been talking about where MySQL HeatWave is a one-stop shop for all your OLTP, OLAP, and machine learning applications. And we have integrated with all the various tooling that you can provide. So I won't go into this. This is not very relevant. This is just an overview. So this is the interesting slide, right? So when we came up with the whole set of features and we're still continuing to build on them, what we target is a couple of things, right? One is we want to automate your entire service life cycle. So starting with system setup, what do you do? How can we ease your system setup? Then the next step is your data loading process. How can we ease that? How can we make it more performant or make it more easy to use? Once the data is loaded, we move on to query execution. So how can we, again, improve that with automation? And finally, in case of failure handling, what can we do to have your system come back up automatically? So in each of these categories, we have a few features. The features highlighted in red here, the shape prediction and the thread pooling are features we have specifically for the OLTP. The features in purple, I guess, are the features specifically for our Lakehouse applications, and most of the others are for OLAP. And as just want to reiterate that our focus was twofold. One is ease of use, and other is performance. And in some of these features automatically happen behind the covers. The user doesn't need to do anything, whereas for some of them, we require user to take the initiative, and we give like recommendations. So this is just a high-level overview of how did we go about building our models. What did we do? So what we do is we realized in order to build any intelligent machine learning model, we need to look at a lot of data. And where do we find the data? So for that, we look at a lot of the InnoDB tables. We look at HeatWave tables. We look at the logs, the statistics provided by the MySQL optimizer, the plans provided by them. We look at the query execution logs in HeatWave, both pre and post. We look at all this data, then we look at the statistics and we extract the relevant statistics. Then we do some feature extraction and feature engineering to build our models. So now for each of these models, it's not necessary that we have a single model for example, auto provisioning, or for example, we have a dictionary size model, or we'll talk about the order data placement model. So it's not necessary we have a single model. What we do is we try to break up our task into smaller models that are more accurate, and then we combine them to serve our purpose. So that's ML model. And then finally, each of these models serves some stage in the service lifecycle. So we'll start with what are the automation or the stuff we did for the OLTP applications. So one of the important things we did was something called as auto thread pooling. So here the premise was once you have a given configuration on the cloud, right, what happens as you increase the number of concurrency or you increase the number of transactions, your output increases, your throughput. But that only increases up to a certain point. After that, what happens is the system starts choking because I have too many requests coming in and it creates resource contention. So what happens is then we suddenly see the throughput drop. And this was very true of MySQL, Aurora, everywhere that we were seeing. So we introduced a feature which automatically introduces some kind of a waiting queue. So what it does is it does adaptive access control of letting the transactions go into the execution window. So it keeps a tab on how much is my workload, how my CPU is busy, and then accordingly it slows down the incoming transactions into it. And as a result, what happens is there is fewer concurrent access, and then I get a better throughput. And this is just to show you an example of the performance we achieved, right? This was a 10 gig TPCC data set that we ran. The data was in the buffer pool, and we did a performance comparison with Aurora and MySQL HeatWave with the auto-thread pooling feature in the picture. So as you see, till about 256 or 512 concurrent users, the throughput of each one of them kept increasing, right? But once the number of users crossed a certain threshold, there was a lot of resource contention. And then the throughput of Aurora, which doesn't have this thread pooling, suddenly starts dropping. And now with in the MySQL HeatWave, because of our control of how we let the transactions into the system, we were able to sustain the throughput. Yeah. Yes, the number of concurrent users. So now this one other feature that we came up with, and this feature is today available only on the cloud service on AWS, is auto shape prediction. So the premise of this is once I have a resource in the cloud, there are three main things, right? What is the CPU available, what is the memory available, and then what is the I/O capacity of my system. And based on that is my throughput. But however, when we talk to users, we talk to a lot of product managers, and we talk to a lot of MySQL tuning experts, and they said for the MySQL throughput, the most important thing is the size of the buffer pool and whether my data fits in the buffer pool. That's the single most important factor. So in enterprise editions, often the user has the capacity to tune the buffer pool. They can increase the buffer pool size if they see their performance is degrading. However, in the cloud, we already optimize that. So based on the shape that we offer in the cloud, there is already the buffer pool size is prefixed, and the user doesn't have a capacity to change it. What they can do if they need more buffer pool is go up a shape. Or if their data is very small, their buffer pool is underutilized, they can go down a shape. But how do they actually know that that's the case? So we introduced this concept called as auto shape prediction, where we actually read a lot of the statistics, and given we monitor the user's workload continuously, and then we are able to predict what's a good buffer pool size for them. And once we decide a buffer pool size, we know which is the shape which corresponds to that optimal buffer pool size. And we recommend a shape. So these are some of the numbers. What we did was we took a number of benchmarks, we ran numbers on them, and as you can see here, not only is the system able to recommend an upsize if it sees a lot of the buffer pool hit rate is very low, that means my data is not in the buffer pool and I have to do a disk I/O. It recommends an upsize. Similarly, if it sees that my data very easily fits in the buffer pool, or everything I'm going is getting 100% hit rate, then maybe I'm over-provisioned, and then it'll recommend a downsize. And then if you see the buffer pool hit rate, right, it increased, and we saw improvement in throughput when we did the upsize. For the downsize case, the throughput remained pretty much the constant. So it results in an end user saving. So this slide, the buffer pool, the shape prediction feature was there even a few months ago. But as of, I think, this week, we added some more functionality in the HCS console. We integrated it very well. so that the user can actually see. And they get a window of a week. So it's a sliding window. They can move the window around. And on the window, they can decide which buffer pool is optimal for them, and they can see the shape. So this is an example of the new HCS console integration. If you see, it says that I have a current shape is a MySQL 4.32, but based on my workload, I'm better off moving to a 8.64. And then this is a summary view. However, there's a buffer pool insights over there. And if I click on that, it gives me more details. It gives me how my workload was changing, what is my buffer pool hit rate, my buffer pool utilization. So these are all just some of the explanations and the performance metrics that we provide. So now we'll move on to some of the features, not all. There was a very exhaustive list of features we have, but I'll just touch upon some of them. So the most key one is starting with the auto provisioning. So as you know, MySQL HeatWave is an in-memory system. So in order to fit all my data, I need to have an appropriate sized cluster. And it's often a challenge for the user. If they provision too large a cluster, they are overpaying. If they provision under-sized cluster, then their data won't be able to load. Or if it loads, their queries won't be able to run. So what we do is we have something called as auto provisioning. And what it does is, in the case of when the tables are already in the InnoDB, we do adaptive sampling of the data in the InnoDB table. And based on that, we are able to recommend what will be the footprint of the data in a HeatWave cluster. And based on the HeatWave configuration available, we are able to say the number of nodes you would require in a cluster. Then this is yet another feature called as auto parallel load and unload. And unload is a feature which we just released again as of a couple of weeks ago. And these are more of ease of use features. What happens is, if you are familiar with HeatWave, in order to load data into HeatWave, it's a multi-step process. We have to go and mark each table as secondary. So that's one statement. Then we have to go and mark saying load the table into HeatWave. So now if you have a schema with hundreds of or even thousands of tables, it becomes a very cumbersome process. So we provide you with this HeatWave load command, which lets you load all your schema. All you can do is provide a schema, and we'll load all the tables in the schema. It has additional flags which let you exclude certain tables, exclude certain columns and stuff. But essentially in one single go, you can load all your relevant tables into HeatWave. And similarly, if you want to unload, we have a HeatWave unload command. So now with the unload, we also have just released an unload advisor. And what it does is, users can sometimes load tables into HeatWave. But after time passes by, maybe that table is no longer used for any of the analytical queries, but users are not aware, and it just takes up memory there. So now what the auto unload advisor does, it looks at the past query history. It does an analysis. And if it makes sure that this table hasn't been used for a certain period of time, it will recommend that you should go ahead and drop it. So now we come to some of the features which are to do with the query execution time automation. And the first one of them is auto data placement. So as you know, MySQL HeatWave is a heavily distributed system. So now what happens when my query is running and I have a join in the query, my data which is involved in the join, specifically the join keys, they need to be co-located. If they're not, what happens at runtime is I have to distribute the data across the nodes, which is very expensive, not just time-wise, but I'm using up a lot of network bandwidth. So what auto data placement does is it analyzes your workload, and it recommends the best placement keys of how you can partition the data across these various nodes in the cluster. And as a result, not only do you save on the network bandwidth, but your queries really improve. And here are some examples. So for example, for TPCH, 1 terabyte and 4 terabyte when we use the placement keys recommended by the advisor, we saw actually performance improvements of about 40%. Then is the auto-encoding. And auto-encoding is a feature which I'm not sure how many people are aware, but when we store string columns on HeatWave, we can either store them as string, which we call as varlen encoding, or we can store them as dictionary encoded columns. And the advantage of dictionary encoded columns are they take up a lot less space on the MySQL nodes. And also there are certain operations which are much faster because we deal with integers while doing them. However, there is a drawback that if your workload has queries like substring or like queries, right? Queries which work on actual string columns, they can be offloaded. So what autoencoding does is it looks again at your workload history and intelligently tells you which columns you'll benefit by encoding as dictionary encoding. I'll speed up a bit. This is the auto query plan improvement. Here again, what we do is we look at past query executions. We store subgraphs. So we don't cache the whole queries. A lot of our competitors do that. They cache the entire query result, and next time a query comes around, they can use the cached query results. Here what we do is we can even cache subset of queries or a subgraph in the query. And that subgraph, if it happens to occur in yet another query that we see in the future, we can benefit from it. And this is auto scheduling. Here, this is if a system has short and long running queries submitted at the same time, we order them so that the total time that a user has to wait is lower. Okay, I will skip. This is the general architecture slide for the MySQL Lakehouse. And here I just want to cover quickly. So what are the autopilot features for Lakehouse? So if you see, there are certain features which were identical to the warehouse case. For example, auto provisioning, auto load, auto query plan, adaptive sampling, all of these are common across the warehouse and the Lakehouse. But there are certain features like the auto schema inference and the adaptive data flow, which are very relevant just to the Lakehouse. And I'll talk about them, and in the context of when I'm talking about the schema advisor, I'll briefly touch upon how we also use the schema inference internally when we do the auto provisioning and the auto load. So the biggest challenge in Lakehouses is our data is in CSV on the object store, right? Unlike the warehouse case where we have a precise definition of my table data, right? My table is already defined in InnoDB, my data is already loaded there. I know what the structure of my data is. But in this case, my data is in CSV format, and the user may not even know what the schema is, and they are interested in us finding out. So what we do in auto schema inference is we sample the data, and that's where we do adaptive sampling. By adaptive sampling it's not random sampling, but we keep sampling the data till we converge, and based on this sampling, we decide the column type, and then we end up recommending that this is the potential. This is a good schema for the data that you provided in the CSV. Now, once we have a schema, what autoload does is now autoload can use this schema. It can decide, because of the statistics that we collected during schema inference, autoload sort of knows what will be the potential footprint of the data. So it can tell you how long it would take to load the data. It can generate the scripts. And auto provisioning can also builds upon the same thing and can now tell you what size of the cluster would you need for your Lakehouse. This is just example slide of auto schema inference where we did the schema inference, and it tells us not just the number of columns, but also their data type and the precision. And it generates the script, so the user can then just use the script to create the table and then finally load it into the Lakehouse. This is one of the last features we did. So as you know, for the lakehouse, we have to read data from the object store. So what we do is the user's data is in the object store owned by the user. We read it from there, and then we also load it into an internal bucket of the Oracle HeatWave. Now what happens is, in this particular case, the buckets are dictated, they're owned by the OCI team, and each bucket, depending on your tenancy, your agreement, has a different bandwidth and RPS provisioned. So if you start exceeding the RPS, you will keep running into out of capacity, or you'll start running into errors. And that really slows down your read or write rate into the object bucket. Not just that, if you continually, within a period of certain X seconds, if you make too many requests, you might just get a timeout and you might never get your data loaded in there. So what we do as part of our adaptive data flow is we monitor what is the RPS and bandwidth of the bucket and how it is being utilized. And if we see that we are like exceeding the limits or nearing the limits, then we slow down the reads and writes automatically. So in summary, I think we just pretty much covered these features. And just to reiterate, the goal is not just performance, but also ease of use in the various stages of the service lifecycle. And yeah, thank you. And